In 1347, a peasant in Norfolk planted wheat in the same field his grandfather had worked. No fertilizer trucks, no chemical inputs, just observation, manure, and rotation. That field produced wheat for another 600 years. Today, the United Nations estimates we have 60 years of harvest left in many farming regions before the topsoil is gone. This is not nostalgia. This is measurable reality. Medieval farmers maintained soil fertility for centuries using techniques we have abandoned. The difference is not technology. The difference is understanding. They understood that soil is not a substrate. Soil is an organism, and organisms must be fed. Today, we are going to rebuild that knowledge. Section 1. The Three-Field Revelation. To understand medieval soil management, we start with the system that revolutionized European agriculture around 800 AD, the three-field rotation. Take a typical manor with 90 hectares, divided into 3 equal fields of 30 hectares each. Field 1, winter wheat or rye, planted in autumn, harvested in summer. Heavy feeders that demand the most from soil. Field 2, spring crops, oats, barley, and critically, legumes like peas and beans. Field 3, fallow. No crops, just wild grasses and grazing animals. Every year, the rotation advances. Field 1 becomes 2, 2 becomes 3, 3 becomes 1. The cycle completes every 3 years. The secret? Nitrogen. Medieval farmers had found a way to capture it from thin air. When you plant peas or beans, small nodules develop on their roots. Inside live bacteria called rhizobia. These bacteria capture nitrogen gas from the air and convert it into ammonia, a form plants can use. This is nitrogen fixation. A single hectare of peas can fix 100 to 300 kilograms of nitrogen per year. Modern farms apply 150 to 200 kilograms of synthetic nitrogen fertilizer per hectare. Medieval farmers had created a nitrogen factory, powered by bacteria, running on sunlight. Cost, 0. But the fallow field was equally critical. Leaving 1/3 of farmland empty seems wasteful. Why not plant all 3 fields and triple production? Because medieval farmers understood rest is regeneration. When field 3 lies fallow, 3 processes occur. First, soil structure recovers. Every plow damages soil aggregates, tiny clumps held together by fungal threads and bacterial secretions. These aggregates create pore spaces for water and air. Plant roots need oxygen. Soil microorganisms need oxygen. When you compact soil through repeated plowing, you squeeze out the air. The soil suffocates. A year of fallow allows wild grass roots to penetrate deep, creating channels. Earthworms tunnel through, mixing layers. Fungal networks rebuild their infrastructure. By the time the field returns to cultivation, the soil structure has recovered. The soil breathes again. Second, organic matter accumulates. Wild grasses photosynthesize carbon dioxide and store it as plant tissue. When winter comes, these plants die and decompose. Their carbon enters the soil. This matters because soil organic matter is the foundation of fertility. It holds water like a sponge, stores nutrients like a battery, and feeds the microbial communities that make nutrients available to plants. Medieval farmers never measured soil organic carbon. They saw the difference. Dark soil meant high organic matter. Light soil meant depleted. They had names for this. Black pits for dark, carbon-rich soil near old settlements. Hunger hell for poor, pale fields that consistently underperformed. Color was diagnosis. Third, animals grazed the fallow field. This was the integration that modern industrial agriculture has almost completely lost. Medieval farming was not just crop production. It was a closed loop between crops and livestock. The animals, cattle, sheep, pigs, converted plant biomass into meat, milk, and most importantly, manure. A single cow produces 20 kilograms of manure per day. Over a year grazing a fallow field, 7,300 kilograms per cow. Spread across 1 hectare, enough to significantly replenish soil nutrients. But manure is more than nutrients. Each kilogram contains approximately 10 billion microorganisms, bacteria, fungi, protozoa. When you spread manure, you are not just adding nitrogen, phosphorus, and potassium. You are inoculating the soil with a workforce of living organisms that process organic matter and make nutrients available to plants. Archaeological evidence confirms this practice. Soil scientists analyzing medieval sites in Germany and England detected steroids and bile acids, chemical signatures persisting for centuries. The data showed livestock manure applied at 10 to 20 tons per hectare annually, concentrated on fields about to be planted with wheat. Medieval farmers created a 3-year cycle: building, harvesting, regeneration. 2/3 of land produced food every year. 1/3 rested and rebuilt. The system was sustainable for centuries. Modern monoculture plants the same crop year after year. Corn in Iowa, soybeans in Brazil. No rotation, no rest. The result? Soil degrades at rates 10 to 100 times faster than it can regenerate. Topsoil that took 500 years to build disappears in 50. Medieval fields produced lower yields, but they produced indefinitely. Modern fields produce high yields for decades, then collapse. The difference between sustainability and extraction, between farming and mining. Section 2. The Legume Revolution. Legumes were not just food. They were soil medicine. Historical records show that up to 8% of medieval fields were dedicated to legumes. This might seem small, but consider the mathematics. A hectare of peas fixes 100 to 300 kilograms of nitrogen per year. Only a portion goes into the harvested peas. The rest remains in plant residue, leaves, stems, and critically, the roots with their nitrogen-rich nodules. When medieval farmers harvested peas, they pulled up the vines but left the roots in the ground. Those roots decomposed over winter, releasing nitrogen directly into the soil. By spring, when wheat was planted in that field, the nitrogen was available exactly when the wheat needed it most. This was precision agriculture, timing nitrogen release to match crop demand. No runoff, no waste, no excess. Modern synthetic nitrogen dissolves rapidly. Plants can only absorb a fraction of what is applied. Studies show 50% or more leaches away, contaminating groundwater and rivers, creating ocean dead zones. Medieval legume nitrogen had 80% efficiency. Most stayed in the field and went into the next crop. How did they discover this without chemistry? Through observation. Imagine you are a medieval farmer. You plant wheat in a field. The yield is poor, the stalks are thin. You try the same field the next year. Even worse, the field is tired. Then one year, by accident or necessity, you plant peas instead of wheat. The peas grow well, you harvest them. The following year, you plant wheat again in the same field. Suddenly, the wheat is vigorous, the stalks are thick, the grain is full. You do not understand why, but you observed the pattern. Peas help wheat. Over generations, this observation was refined. Different legumes tested, timing adjusted. The practice spread from manor to manor. By the 13th century, it was standard agricultural knowledge across Europe. They did not need to understand nitrogen fixation biochemistry. They just paid attention to what worked. This is empirical science, knowledge built from observation rather than theory. Compare this to synthetic nitrogen fertilizer, invented in 1909 by Fritz Haber. The Haber-Bosch process now produces 150 million tons per year, feeding approximately half the world's population. But it requires immense energy. 1 ton of ammonia consumes 2 tons of natural gas. The process releases significant carbon dioxide, and overuse causes environmental damage medieval farmers never imagined. Medieval legumes achieved similar nitrogen fixation using only sunlight and bacteria. Energy input, photosynthesis, carbon footprint, negative. The plants removed carbon dioxide from the atmosphere. Modern agricultural science is now returning to legumes. Cover crop research shows legumes can reduce synthetic fertilizer needs by 30 to 70% while improving soil structure and increasing biodiversity. We are rediscovering what medieval farmers knew, slowly, through decades of research. They figured it out by watching peas grow. We figured it out by destroying soil and then studying why it stopped working. Section 3. The composting system. Medieval composting was not throwing scraps in a pile. It was controlled decomposition, a hot process that transformed waste into stable soil amendment. The system had precise rules, documented in 13th century agricultural manuals, rules about layering, rules about moisture, rules about timing. A typical compost heap started with coarse straw, 20 centimeters deep, providing structure and airflow. Next, fresh manure, 15 centimeters, introducing thermophilic bacteria that thrive at high temperatures. Third, plant waste, leaves, vegetable scraps, crop residues, 10 centimeters deep. The pattern repeated: straw, manure, plant waste, straw, manure, plant waste, until the heap reached 1.5 meters high. Then, 3 days undisturbed. During those 3 days, internal temperature rose dramatically. Modern composting science explains why. When bacteria decompose organic matter, they release energy as heat. In a well-constructed pile with the right carbon-to-nitrogen ratio, approximately 30:1, bacterial activity raises internal temperature to 60 to 70 degrees Celsius. This high temperature serves two critical functions. First, it kills weed seeds and pathogens. Any seeds present in plant waste are sterilized. Any disease organisms are destroyed. The compost becomes safe to apply to fields without introducing problems. Second, the heat accelerates decomposition tenfold compared to ambient temperature. A pile requiring 6 months at room temperature is ready in 6 weeks with hot composting. But medieval farmers did not just build the pile and leave it. They monitored it, and they intervened based on observation. Historical texts describe testing the pile with a wooden stick pushed deep into the center. If the stick came out hot to the touch, the pile worked correctly. If cold, something was wrong. The pile needed more nitrogen-rich material. If the stick came out too hot, almost burning, the pile needed water. Excessive temperature meant decomposition proceeding too fast, potentially losing nitrogen as ammonia gas. Medieval farmers were regulating microbial thermodynamics without thermometers, without microbiology textbooks, just sticks and observation. After 3 weeks, the pile was turned. The outer layers moved to center, center moved to outside. Turning introduced fresh oxygen, reactivated bacterial decomposition, ensured uniform processing. The pile was turned every 2 weeks for 6 weeks total. At the end, the compost was ready. The material was dark brown, crumbly, and smelled like forest floor. Chemical analysis of medieval compost from waterlogged archaeological sites shows carbon-to-nitrogen ratio of 12.1, ideal for plant growth. The material contained stable humic compounds, long-chain carbon molecules that resist further decomposition and provide long-term soil structure. Most impressively, analysis of fossilized bacterial DNA from medieval compost shows diverse microbial communities: nitrogen-fixing bacteria, phosphate-solubilizing fungi, cellulose-decomposing actinomycetes. The medieval compost pile was not waste disposal. It was microbial cultivation. Modern composting follows the same principles. Industrial facilities use temperature probes and forced aeration to achieve what medieval farmers achieved with sticks and observation. The knowledge was never wrong. We just added instrumentation to confirm what they already knew through practice. Section 4. Reading soil. Medieval farmers possessed 3 forms of soil literacy. 3 ways of assessing soil health without instruments or laboratories. Just perception, refined through generations of observation. The first sense was color. Soil color was not merely aesthetic, it was diagnostic, and medieval farmers had developed a sophisticated color vocabulary. Black soil indicated high organic matter content. Historical records described these soils as fat or rich. Fields with black soil consistently produced the highest yields. These were premium lands, often controlled by the Lord or the Church. The darkness came from decomposed organic matter, specifically humic substances, complex carbon compounds formed during long-term decomposition. Modern soil science quantifies this as percent organic carbon. Medieval farmers quantified it as shades of black. The knowledge was equivalent. Brown soil indicated moderate fertility. These were working fields where most crops were grown. Brown meant the soil had some organic matter but needed regular inputs to maintain productivity. Gray or pale soil indicated exhaustion. These were the hungry fields, lands that had been overcultivated and depleted. Medieval texts recommend these fields be left fallow for 2 years, not 1 to allow recovery. Medieval farmers learned colors from their fathers and associated each with yield outcomes. Modern soil science uses the Munsell color chart with over 100 color categories. Medieval farmers never needed a chart. They adapted practices accordingly. The second sense was texture. Medieval farmers assessed soil by feel. They would take a handful of soil, add a small amount of water, and manipulate it between their fingers. Sandy soil felt gritty. Individual grains were visible and distinct. This soil drained quickly, preventing waterlogging but drying rapidly during drought. Crops grown on sandy soil needed frequent irrigation. Loamy soil felt smooth but not sticky. It could be formed into a shape but crumbled easily. This was the ideal texture, combining good drainage with good water retention. Medieval texts describe loam as the blessed soil. Clay soil felt sticky and plastic. It could be formed into shapes that held together. This soil retained water extremely well, sometimes too well. It was heavy to plow. It became hard as brick when dry. But it was naturally fertile, rich in minerals. Medieval farmers adjusted crop selection based on texture. Sandy soils received rye and oats, crops tolerant of dry conditions. Clay soils received wheat and barley, crops that could handle wet conditions. Loamy soils received the most valuable crops because they suited almost everything. Modern soil science uses the soil texture triangle, classification based on sand, silt, and clay percentages. You can send samples to laboratories for particle size analysis. Or do what medieval farmers did, knead the soil and feel the difference. The third sense was observation of indicator plants. Medieval farmers knew that certain weeds revealed soil conditions. Nettles growing densely indicated high nitrogen levels. A field overrun with nettles was a field ready for planting heavy feeders like wheat. Horsetail indicated waterlogged, poorly drained soil. Fields with horsetail needed drainage improvements before productive farming. Clover appearing spontaneously was seen as a blessing. It indicated the soil had active nitrogen-fixing bacteria. The clover could be plowed under as green manure to further improve fertility. Thistles indicated compacted soil. Their deep taproots could penetrate hard layers that crop roots could not. A field with thistles needed deep plowing to break up compaction. This was botanical diagnosis, reading plant communities to understand soil conditions. Modern soil science calls these indicator species. Medieval farmers used them to decide when to plow, rest, and fertilize. Modern agriculture tests soil in laboratories. Nitrogen levels measured with sensors. Decisions made based on numbers, not observation. The numbers are more precise, but precision is not always accuracy. A laboratory tells you total nitrogen content, but not if that nitrogen is available to plants, not if your soil structure allows roots to access it, not if your microbial community is healthy enough to cycle it. Medieval farmers could not measure nitrogen in parts per million, but they could look at their wheat and know if soil was providing what plants needed. If the problem was nitrogen, they planted peas. If the problem was compaction, they plowed deeper. If the problem was acidity, they applied lime. They responded to what they saw, not what a test said. And their soils remained productive for centuries. Section 5. The Marling Secret. Marl is a mixture of clay and calcium carbonate, a naturally occurring sediment found in certain geological formations. It looks like chalky clay, pale gray or white, often found in layers beneath topsoil or near ancient lake beds. Medieval farmers in England, France, and the Low Countries transported marl to fields and spread it at 20 to 40 cubic meters per hectare. Back-breaking labor. A cubic meter weighs 1.5 tons. Why would farmers expend so much effort? Fields treated with marl produced better yields. For decades, sometimes generations. Modern soil chemistry explains it. Calcium carbonate neutralizes soil acidity. Soils become acidic through several natural processes. Decomposition of organic matter produces organic acids. Rainfall leaches calcium and magnesium from soil, leaving behind hydrogen ions. Crops extract calcium and magnesium, further depleting the soil. As soil becomes acidic, problems occur. Aluminum and manganese, naturally present in soil, become soluble and reach toxic concentrations. Phosphorus, an essential nutrient, binds to iron and aluminum, becoming unavailable to plants. Beneficial bacteria and fungi decline. Result: declining yields even with adequate nutrients. Nutrients are present but locked up, chemically unavailable. Calcium carbonate from marl reacts with acidic soil. Carbonate neutralizes hydrogen ions, raising pH. Aluminum and manganese become insoluble again, non-toxic. Phosphorus is released from iron and aluminum complexes. Microbial communities recover. Medieval farmers did not understand pH chemistry, but they observed that certain fields, particularly those farmed intensively, responded dramatically to marl. 13th century agricultural manuals document detailed instructions. How to identify good marl: it fizzes when you drop vinegar on it. The carbonate reacting with acetic acid, producing carbon dioxide bubbles. Where to dig for marl: in white or gray clay layers, often 1 to 2 meters below the surface. How much to apply? Enough to make a visible white dust on the field surface after spreading. This meant 30 to 50 tons per hectare, which modern soil science recognizes as appropriate lime rate for moderately acidic soils. Archaeological evidence from medieval sites in England shows elevated calcium levels, chemical signatures of historical marling persisting centuries after application. The practice was not universal. Marl is not available everywhere. But where marl was accessible and where soils were acidic, marling was standard practice. The Domesday Book, a land survey of England completed in 1086, documents marl pits as valuable estate features. Manors with marl pits were assessed at higher value than those without. Modern agriculture industrialized this practice. Agricultural lime, calcium carbonate, or calcium oxide, is produced from limestone quarries and spread mechanically. Chemistry identical. Mechanism identical. Result identical. We did not improve the technique. We just made it faster and more widely available. But we also created dependency. Modern farmers buy lime from suppliers. Medieval farmers dug marl from their own land or nearby deposits. Modern agriculture requires external inputs and supply chains. Medieval agriculture was self-contained. When those supply chains break, modern agriculture struggles. Medieval agriculture continued. The permanent versus the extra-active. The story of medieval soil management is ultimately about value. What do we value? Short-term productivity or long-term fertility? Extraction or regeneration? Medieval farmers had no choice. Their technology forced them into slow, laborious practices. But those practices, refined through centuries of observation, maintained soil fertility indefinitely. We have made different choices. We have harnessed fossil fuels to subsidize agriculture. We synthesize nitrogen. We mine phosphorus. We have fed 8 billion people. But we have borrowed from the future to feed the present. Every ton of topsoil lost. Every % of organic matter depleted. Every microbial community destroyed. These are debts accumulating. The United Nations estimates 60 years of harvest remaining. That is 60 years to figure out how to feed 8 billion people without destroying the soil that feeds them. Medieval farmers had solved this, not perfectly, not with modern productivity, but they had solved it. Understanding what they knew How they learned it and why we abandoned it is not nostalgia. It is necessity. Every time a farmer plants a crop, they are making choices. Choices that echo across decades, across centuries. Medieval choices created soil that lasted 600 years. Modern choices create soil that lasts 60 years. Perhaps in understanding what has been lost, we can begin to ask what might be reclaimed. Not a return to medieval technology, but a return to medieval wisdom. The understanding that soil is not a substrate. Soil is an organism, and organisms must be fed. Thank you for watching.